Ladies and gentlemen, let's continue with our chapter on the fundamentals of convection. This is chapter 6, and with the previous lecture, we've introduced the Nusselt number, and there was an example where I referred to that I gave a few values, and I think I wrote the temperature is equal to 100 watts per square meter degree Celsius, and the characteristic length was 8 meter, and then we looked at air as well as something else, another type of fluid with K values which were in the order of magnitude of 400 was the one, and the other one was 0.03, the K values. This was, of course, a writing error. This shouldn't be the temperature, it should have been the heat transfer coefficient, but I hope you could figure it out. Okay, so let's just go back to the Nusselt number. I just want to look at the significance of it, the physical significance of the Nusselt number, and what it really means. So let's suppose we've got fluid layers or two flat walls at temperatures of T1 and T2, and they are apart a distance L, and we've got the heat transfer rate from T1 to T2, so this temperature is higher than that temperature. Then in general we can say if, firstly, the fluid is in motion. The fluid in motion, so maybe the flow is from left to right or from right to left, then we can say that the heat flux of convection is equal to the heat transfer coefficient multiplied by delta T, which will be the heat transfer coefficient multiplied by the temperature difference, T2 minus T1. Okay, now remember, the heat flux is always equal to the heat transfer rate divided by the surface area, so the units would be watts per square meter for the heat flux. However, so this is in the case if the fluid is in motion. That's the first case. The second case, let's look at the fluid is stationary. Is stationary and G is equal to 0. There are no gravitational forces, therefore there cannot be any buoyancy here in terms of buoyancy forces. The temperatures, even although the density of the fluid would decrease, there are no buoyancy forces, so there cannot be any fluid motion because of natural convection. Then the heat transfer will only be by conduction. Heat transfer by conduction, and if it's by conduction, it would be equal to K multiplied by delta T divided by L. Delta T, of course, is equal to the temperature difference. Question?
H is of the liquid.
I beg your pardon?
The H is of the liquid.
Yep.
And so the plate doesn't matter what
no.
material the plate
Yeah, no. So the K would be the K of the fluid here. So it would be the K of the fluid. So the heat transfer is from the inside of the plate to that side of the plate. So the material of the plate we do not take into consideration at the moment. So If we now look at the ratio of the convection heat transfer divided by the conduction, then it would be equal to the heat transfer coefficient multiplied by delta T divided by K delta T divided by L, which is equal to the heat transfer coefficient multiplied by L divided by K of the fluid, okay, which is equal to the definition of the Nusselt number. It means, therefore, the Nusselt number represents the enhancement of heat transfer. Okay, heat transfer, I'm just going to refer to it as HT, the heat transfer. And there are different scenarios. So if the Nusselt number is equal to 1, then it means the heat transfer is by conduction only. The heat transfer is by conduction only. It therefore means the Nusselt number must always be larger or equal to 1. Therefore, you must always remember that if you do a calculation for a Nusselt number, and you would get a Nusselt number of 0.5, then you must immediately know somewhere you've made a mistake. It cannot be. So the Nusselt number can be 1 if it's only conduction. If the Nusselt number is 2, it means that the heat transfer would be double than that of conduction because of the fluid motion. And in general, if we keep on increasing the fluid motion, the heat transfer would increase, the Nusselt number would increase, so the Nusselt number tells us with how much the heat transfer is being improved, being enhanced. So a Nusselt number smaller than 1 is not possible. It's a fundamental error if you do a calculation with a Nusselt number smaller than 0.1 and you accept it as a correct value. Right, paragraph 6.2 is about the classification of fluid flow. And the classifications that are being discussed are work that you've already done in fluid mechanics with your previous module, and that is the classification of viscous versus inviscid flow, internal versus external flow, internal versus external flow, compressible versus incompressible flow, laminar versus turbulent flow, natural versus forced convection, steady versus unsteady, one-dimensional flow, two-dimensional, and three-dimensional flows. I assume you're all familiar with that, so I'm just going to revise it very quickly without going into it in too much detail. But let's consider a case of a turbine on an aeroplane. And a turbine has three components. So there is the air inlet. And let's suppose this aeroplane is flying at a Mach number of 0.2. Mach number of 0.2. And this is the one wing of an aeroplane. And let's see how far can we go back into the revisions of fluid mechanics to relate it to this problem, as well as the problem where we're going to have a bird strike. A bird strike is when a bird goes right through the turbine of the aeroplane. Okay, so in terms of, firstly, the density as a function of time. Let's suppose there is point 1, a measuring station, and there's point 2, point 3, and there's point 4. Okay. For in case you don't know, that is the compressor. So the air is being compressed. Then we've got the combustion chamber, where the fuel and the air is being mixed. The temperature and the pressure increases in the combustion chamber, and then it expands through the turbine, and that is what generates the thrust of an aeroplane. So if we would typically now look at measuring station 1, then the density of the air would be approximately not 1, lower than 1, so it depends on the height, but let's suppose it is equal to 0.5. So there is a density of 0.5, and the units would be kilograms per cubic meter. So that would be the density, and that is how we will be measuring the density there. It will not change, it will be the same, except for later on when we're going to get the bird strike. Okay. Then at point 2, the density there will be higher because this is the compressor. It compresses everything to maybe, let's use an arbitrary value of 3. Okay, so that is how that is going to be. Oh, point 2 should be there also, sorry, in between. Let's suppose that is 1.5, which means that the compression ratio is approximately 3. Normally, I think it is higher, but these are just arbitrary values. Then, at point 4, it will be expanded again. Sorry, that would be at the outlet of the turbine. So the density there would again be low. Let's suppose that is measuring station 4. 1, 2, and 3, the different measuring stations. So the first thing that we can learn here is that the flow is steady. It's steady because the density is not a function of time. It stays constant. And therefore, it is steady. Later on, when we're going to get the bird strike, then it's going to be unsteady. Also, what we now can see is that at measuring station 1, we can consider the fluid to be incompressible. It's incompressible. It hasn't been compressed. It's this atmospheric air. And if you keep on measuring the density there, it is not going to change. The same at measuring station 2. If you stand there and you would measure the densities all the time, it's going to be the same. Except now if you're a molecule and you move right through the turbine. If you do that, you're going to go through a process where the flow would be compressible. It's going to be compressed. And then here on the outside again, it would be incompressible. Okay? We can also distinguish here between external flow. The flow is on the outside of the turbine. Here it goes right through the turbine, so that is considered as internal flow. If you look at the flow molecule going through the turbine, it is inside two boundaries, and therefore it is considered as internal flow. And here on the outside, the flow would again be external flow. So where I've plotted the density here as function of time, I can now plot the density as a function of x, where x is being measured from that inlet. Okay. And there would be x equals 0. If we would go upstream, then the density is going to be a constant. Then it is going to go through the compressor, through the combustion chamber, and it will be decreased again as it expands through the turbine, and it would do something like that. So the density is a function of x. Okay. So therefore it goes through a process of being compressed and then being expanded. So we cannot consider that as incompressible flow. It is compressible. So it all depends where you're measuring. If you are sitting here at the inlet and you measure the density all the time, it's going to stay the same. And therefore you're going to report back it's incompressible flow. However, if you're a molecule going right through, then you will experience the process of not being compressed, then being compressed, lots of heat transfer, it's going to be heated up, and then you're going to expand through the turbine. Now let's now suppose the case of the bird strike. So here comes the bird, and it goes right through the turbine. For in case you don't know, bird strike is of course a very risky thing for any aeroplane during takeoff. Because of that, there were quite a few accidents already. And what they do typically, if they design a gas turbine engine for an aeroplane, is they do experiments. And in the experiments, they do not use live birds, but they use frozen chickens. And it should be able to go right through the turbine or right through the aeroplane. There might be some losses. It might damage it, but they shouldn't lose the aeroplane. So there's a lot of research that has been conducted on that. Now, for those cases, if we now look at the density as a function of time. Okay. If you sit here and you measure the density, you're going to get a constant reading, and then suddenly you're going to get the bird strike. And the density is going to increase for a split second, and then it is going to go back if the turbine, if the engine still functions, and it's going to recover. Okay. At point two is going to experience the bird a little bit later. Okay, then it's going to go back, and then point 3, a little bit later, going back, etc. Therefore, the flow up to here was steady state. That flow is also steady. But for these conditions, the density was a function of time. Previously, it wasn't a function of time. Therefore, we've considered it as steady state. In this case now, the flow would be considered as unsteady. Okay. So that is a short summary of external flow and internal flow. Steady versus unsteady. Compressible against incompressible flow. Okay? With one problem. all the possible scenarios. Are there anything that's unclear to you in terms of this fluid mechanics which you haven't understood up to now and still do not understand? Good. Right, now let's go to paragraph 6.3, which is about the velocity boundary layer. The velocity boundary layer. And this is also revision, and I'm going to revise it because this velocity boundary layer, we are going to relate it to the one of that happens during heat transfer. These two different ones, but lots of similarity. So if this is now a flat plate, and this is the velocity distribution, which is uniform. With uniform, we mean it is the velocities are everywhere the same if we measure in a horizontal y direction. And then what is going to happen is three different boundary layers are going to form. With firstly, this first part, which is considered as a laminar flow, this part, which is considered as turbulent flow, and this part is considered as the transitional flow regime. How the flow changes from laminar to turbulent, that is known as the transitional flow regime. And what we're going to do now is we're going to look at the velocity distribution typically here at A, and we're going to compare it to the velocity distribution at B. Therefore, the velocity distribution during laminar flow in comparison with the velocity distribution during turbulent flow. This distance is known as the critical length, or then the position where the flow will not be laminar anymore, it will change to transitional flow and or turbulent flow. So if we now go and enhance this velocity distribution, if that is equal to V, and let's suppose that is 100 meters per second, and we would draw this arrow to be 100 millimeters or 100 centimeters, then that would be 100 up to a point where it is 99. And it will typically do something like that, all the velocity distributions. So let's suppose that is 80, and that is 30, and here the velocity is equal to 0. It is known as the no-slip boundary condition. So there's no slip there, the velocity goes to 0. So in terms of this example, what you've learned in fluid mechanics is that boundary layer thickness is where delta is equal to 0.99 V. 0.99 times the free stream velocity. Let's do that. V infinite, it is the free stream boundary, free stream velocity. Now in this case, we said that the free stream velocity is 100 meters per second. So it is very easy to determine the boundary layer thickness. All we do is we start with something that, an instrument that can measure the velocity. It's 100, 100, 100 until, here it's 99. So where it is 99% of the free stream value, that would be equal to delta, or the boundary layer thickness. So 99% of the free stream value. So I've used 100 meters per second, but if I would use 10 meters per second, it would be where the velocity is equal to 9.9 meters per second. Okay? Is that clear to everybody? What is also important is that this gradient here, that gradient determines the wall shear stress. And the wall shear stress is equal to the viscosity multiplied by du dy, where y is equal to 0. And this is equal to du dy. It is that gradient that I've drawn there in yellow. So we know that mu is the dynamic viscosity, and it is, we can also, and we can also write it as the kinematic viscosity, which is the viscosity divided by the density. Okay, so this is the kinematic one, the kinematic viscosity, and that is the dynamic viscosity. We will interchange this in terms of how it is being used, and the viscosity values differs for different mediums as a function of temperature. So normally for liquids, the viscosity would decrease with temperature, while with gases, there's an increase in the viscosity. So here we can see the viscosity as a function of temperature. Therefore, in your textbooks, you need to take that into consideration. If we typically look just for different values, let's say medium, and the viscosity with unit kilograms per meter second for different mediums, then for air, the viscosity is equal to 0.12345 very low. And then water would be 0.001. Engine oil would be 0.3. And glycerine would be equal to 1.52. So between air and water, you can see there's almost 3 orders of magnitude difference in the viscosity values. Going to oils, another order of magnitude again, and to glycerine, 1.52, just to give you a feeling for different values. And these were at 20 degrees Celsius. Remember, the viscosity is a function of temperature, so I've given you just a few values at a temperature of 20 degrees Celsius. If we now look at typically the temperature dependence, if we look at 0 degrees, 50 degrees Celsius, and 100 degrees Celsius for air and water, then air would be about 1.729. I don't think this is correct, but in any case, just go and check that value, please. And at 50, it would be 1.96 in comparison with 0.54, and at 100, it would be 2.2, and that would be 0.297, and that value would be equal to 10 to the minus 5, and that value would be equal to 10 to the minus 3. So that is in terms of viscosity as a function of time and for different mediums. Now what is very important is that this velocity distribution is for laminar flow. That is for A, so it's for laminar flow. And at B, if the flow is turbulent, the velocity profile would look totally different. So that would be for B. For B, we will find that the velocity profile is constant, and then we'll do something like that. This velocity distribution is more parabolic. Again, that would be equal to the free stream velocity. Let's suppose 100 meters per second. If we would keep on going down, 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 up to this point here, there we would measure 99 meters per second. Then again, that would then be the boundary layer thickness delta. And again, this gradient will determine the shear stress. This gradient there, which is equal to du dy, that would determine the shear stress for us. Okay. If we look at flow through a tube, a pipe, then last year you've looked at the friction factor as a function of Reynolds number, the relationship between friction factor and the shear stress. I will get to that a little bit later, but the two is directly related to each other. So typically in the laminar flow regime, the friction factor is 64 divided by the Reynolds number. So it's a straight line on a log-log curve. So you'll get something like that. And then in your Moody charts at the back of your textbook, you'll find that as epsilon divided by d is equal to 0. So that's the case for a smooth tube. And here, you will see in your textbook, it shows something like that. Which means that the solution is not known. Now, since Moody did these experiments, we know a lot more now, and we've done many more experiments, and we have found that the behavior here is being determined by the type of inlet that is being used. And an inlet can be a very square edge, or it can be one that is very smooth. And the result of that is actually that inside here we've got a transition area which does something like that. Now, what is the difference in terms of if we would, in this case, do measurements at point 1 and point 2 for the velocities as a function of time? If we would take measurements of the velocity as function of time with the most accurate instrument that we can, then at point 1 we are going to measure the flow like that. At point 1 it's going to be steady, the same value all the time. It's not going to be a function of temperature. The flow is laminar. It means it moves in laminar layers and on top of each other, and they are not being bothered a lot by other molecules and or flow in the immediate flow regime. So that would be at point 1. If we keep on increasing the velocity, we get to this transition point. We would go over the transitional flow regime and into the turbulent flow regime. Now, if we take measurements at point 2, the measurements is going to do something like that. It's going to fluctuate a lot. Okay. although the average value would be constant. The average is constant, so if you would enlarge this, you will find that the fluctuations are typically doing something like that, and these are called the fluctuations. So the velocity, the average velocity, or the velocity, is equal to the velocity plus the fluctuation. But if you do the integration, you will find that it is equal to an average velocity which is constant. That would be what typically happens in a smooth tube. If you've got the case for a flat plate, then there are some similarities. And the similarities would be best shown not by the friction factor, but by the wall shear stress. Again, I will get to the relationship of the two just a little bit later. And in this case, the shear stress would do something like this. It would increase and then do something like that. And that would be as a function of x. So the shear stress would actually decrease up to a certain point. And for a flat plate, that transition would occur approximately at 300,000 to 600,000. That is where transition would occur. For a tube, transition would occur at a Reynolds number of 2,100. So the Reynolds number is dependent on the geometry that is being considered. It would vary significantly between internal flow through a tube and external flow over the aeroplane wing of an Airbus. Yep. Yes, that's the Reynolds number range. So here the Reynolds numbers would go into transition at approximately 2,100. For a flat plate, it's about 300,000 to 600,000. It's different. So there's not one Reynolds number that are being used for all geometries to determine the transition from laminar to turbulent flow. Ladies and gentlemen, can you quiet down, please? We are not finished yet, and there's a question there. Can I get your attention, please? Yep.
Why did you say that the shear stress is a function of x? It's a function of the Reynolds?
It's a function of both. Okay. This would be the average. So if we would now go and check the average value, that would be tau average of the wall. So the wall average would stay constant for a specific Reynolds number, a specific free stream velocity. But the behavior, as you can see, in terms of the shear stress, the local values as you go down the plate would vary significantly. And I would address that in the next lecture. But you can also just go back to your fluid mechanics and go and read it again. It is quite important. Ladies and gentlemen, thank you very much.